Okay, so in this video now we're going to basically repeat the previous problem, but in addition to that we have a rough patch. Okay, a rough patch of some distance d, and the question is, hey, what is the minimum x required such that it just completes the loop? Now if the question was not just completes the loop, it's just what find the speed at the top of the loop given the x, then you'll still follow the same line of reasoning. Okay, it's just that your order of progression will be different. So in this case, what we first are going to do, just like we did in the previous two problems, is find the speed at the top. Okay, by now I hope that you're all able to find the speed at the top, and that you recognize that to just complete the circle, the speed at the top is square root of r times g. Okay, if you do not remember this, just watch the previous video, and what I would like you to do is just make sure that you calculate this out so that you know that you can do this in your sleep. Okay, find this value. Now what we're going to do is, since we know the speed at the top, we could go along different ways. One is we could now take our initial to be where the spring is compressed, the final to be the the top of the loop, and then we could do the work, find the work done by the non-conservative force, and just do WNC equals MEF minus MEI. Another approach would be to find the speed first at the bottom and then do WNC equals MEF minus MEI between the the spring leaving the block and the block going on the other side of the rough patch. Okay, it's all you could approach this problem any way you want. In this case, we'll just use the more direct way, where since we know that the object is in the beginning it is compressed by the spring, so all that energy is going to be utilized in doing work against friction and then giving it some energy at the top of the loop. So we will use WNC equals MEF minus MEI. Okay, so we'll do this with one step using this, and then I'll also do a breakdown and figure out how we can do it one step at a time, and it'll also be a quick review of all the earlier concepts. So what we know is that friction is doing work, WNC, so the mass of the object is m, so the force of friction, okay, we're going to use FD cosine theta, so the force of friction happens to be mu k times mg, so this is the force of friction, multiplied by d multiplied by cosine of 180. Okay, now the mechanical energy final is equal to 1/2 times m times square root gr square plus mg times 2r. Okay, the spring has no energy at that point, so I'll just put a 0 for the spring energy. Okay, and the initial is all the spring, so it is 1/2 k times x square, and our goal of course is to find x. Okay, so the left hand side simply becomes negative mu k mg d, and the first term on the right hand side, okay, if you've guessed correctly, it becomes 5/2 times mgr, and I have minus 1/2 k x square. Okay, so from now from this I can do 1/2 k x square equals 5/2 mgr plus mu k mg d, and now I can write x square is equal to you can multiply both sides by 2, so I'll do 2 times 5/2 mgr plus mu k mg d, and then also divide by k, so I get kx equals square root of 2 over k times 5/2 mgr plus mu k mg d. Okay, so this is the one, this is the direct way of doing the problem. If you wanted to, on the other hand, okay, you could have first found the speed at the bottom. Okay, first find this, so let's just call it some v2. Then what we can do is we could then find the speed, say just before it enters the rough patch, so it's v1, and then by doing mechanical energy conservation we could find x by knowing that 1/2 kx square, okay, 1/2 kx square is equal to 1/2 mv1 square. Then for the rough patch we would have an equation that says that the 1/2 mv2 square minus 1/2 mv1 square is equal to negative mu k mg d, and to find the speed at the bottom here, we're simply going to do MEI equals MEF, which is 1/2 m v2 square is equal to 1/2 m square root gr square plus mg times 2r, and so you can get all the components from that part. Okay, so that's a little problem that's slightly involved, but again, by using all the earlier concepts, we can take care of this.